Hi, and today is our final lecture regarding for the entire course of digital signal processing, and this lecture is going to be based on audio fingerprinting. Now, this lecture is the final question on your final exam, and that entire last question will come based on this lecture. So it's important that you pay attention to specific points in this lecture to figure out what it is that actually will come on the final exam itself. So the situation for an audio fingerprinting system is that you may hear music playing somewhere, but you actually don't recognize who the artist is or what is the name of the song. And it's too cumbersome to call the radio station because most of the times they don't tend to pick up the phone, or you gotta wait very long before they answer. So in that case, it's kind of useful to develop some kind of phone app that can actually identify the song that's being played and can tell you who's singing it and what's the name of the song. Now, there are two methods that can be used, which are the fingerprint extraction method and a fingerprint search strategy, and we'll be discussing both of them in particular. Because after we extract the fingerprint, we actually need to figure out how can we search it and find a match to get an accurate result as to which song is playing and who's singing it, and what's the name of the song and so forth. So general fingerprinting systems tend to be like really old, and they have existed for like many years. And in 1893, Sir Francis Galton proved that no two fingerprints of human beings were alike. And then 10 years later, Scotland Yard implemented it for identification of people, especially when they were doing criminal investigation scenes. Even older than that, like all the way back in the Chinese dynasty, the emperors used to use thumbprints to sign important documents, and these thumbprints were basically unique identifiers as to identify which emperor signed which document and so forth. Now, a human fingerprint basically differs from any textual summary, and it really doesn't allow for reconstruction of other aspects of the original. And in using this kind of fingerprint idea regards to multimedia objects, it is formed on the same basis that the fingerprint is basically a unique identifier. So this is the only fingerprint for this particular song or for this particular audio, and it cannot differ from any other thing regarding for different audio and so forth. And once we have this unique identifier, then we can use it for search and retrieve applications, because then it makes this process easier. And the objective of any multimedia fingerprinting system is that we need to establish perceptual equality of two multimedia objects. And these fingerprints that are used will basically serve as an index to the metadata, where the metadata will be like the artist's name, the title of the song, what genre it is, and so forth. Now, there are a lot of advantages of using fingerprints over the multimedia content itself. And some of them are basically that it's reduced memory and reduced storage requirements. There's a very efficient comparison because perceptual irrelevancies are removed. And there's quite efficient searching because the dataset tends to be smaller. And we will see basically a little bit later on why fingerprints can be compressed to make this searching more efficient and faster, while maintaining the same high level of accuracy. So an audio fingerprint can be seen as a short summary of any audio object, and is analogous to a cryptographic hash function known as H, where H maps to an unusually large object X to an unusually small hash value. And these functions basically allows comparisons of two objects, or two large objects, X and Y, by comparing their respective hash values. And typically, by comparing these respective hash values, there's a low probability of error doing this comparison. However, cryptographic hash functions are not good for fingerprint functions because we're interested in perceptual similarity. And the reason for this being is that if we have two different quality versions of the same song, it sounds similar to the human auditory system, but their waveforms actually are quite different. And hash functions are based on basically the waveform itself. So once we have two different waveforms, a hash match is impossible. And hashes are really not good for perceptual similarity. So any model for perceptual similarity in this case tends to be fundamentally not possible. However, perceptual similarity is not transitive, but there's a way for us to model perceptual similarity by mathematical equality of fingerprints to get such a relationship, which will lead to the construction of a fingerprint function or fingerprint algorithm that we're going to be seeing in the next few slides. Now, some applications that actually have been done using multimedia fingerprinting is like for broadcast monitoring, where this process has been done quite manually in the past by humans listening to broadcasts and figuring out what people have said and adding their respective metadata. But more modernly, it has been used in applications like Shazam for identification of songs. Before Shazam was invented, the copyright industry was using it to filter out songs from popular file sharing applications which were deemed illegal at the time. And this was quite important for finding out, like, okay, who's illegally sharing copyrighted song material and so forth on these networks. It's also used for, like, figuring out which versions of songs that you may want, because let's say there's the original song and then there's a remix. This filtering technology can differentiate between the two and so forth for you to guess which one you actually want. To generate the fingerprint system parameters for any audio system would be these 5 parameters here. So the first one would be robustness, and this will determine like how corrupt the signal is if we can still find a match. The reliability, meaning that how often do we find a correct match. The fingerprint size is being how much storage is required for storing each fingerprint, which is determined for the match. The granularity, meaning how many seconds of audio is needed to identify any audio clip. The less seconds of audio, and we're still maintaining the same high level of accuracy, the better. And the search speed and scalability, basically meaning the speed at which your application responds to finding the fingerprint in the fingerprint database. Now, these 5 basic parameters have a large impact on each other. For example, if lower granularity is required, a larger fingerprint extraction is required to achieve the same reliability. And as such, a false positive rate, meaning that it finds an incorrect result, it's inversely related to the fingerprint size. So, if we have a smaller fingerprint size, we tend to have a higher false positive rate, and if we have a larger fingerprint size, we have a lower false positive rate. Now, the guiding principles for audio fingerprinting extraction basically needs to capture the relevant perceptual features. And the question we tend to ask is, what kind of features would tend to be more suitable? So typically we look at jaw, beats per minute, and something referred to as mood, which is somewhat subjective in nature. The non-semantic features tend to be the mathematical nature, which we tend to base our algorithm on, which are referred to as audio descriptors. And because semantic features are more subjective in nature, this means they are also generally more difficult to compute than non-semantic features. And they aren't universally applicable because things like beats per minute don't actually apply to classical music. Now, a digital fingerprint can be represented as a bit string. And because it's a bit string and is digital in nature, that means we can use similarity measures using addition, subtractions, and multiplications. Also, because the fingerprint streams are digital, this can be actually broken into small atomic intervals referred to as some fingerprints or frames. And for the rest of the lecture, we'll be referring to these broken segments of this fingerprint as frames itself. So this actually brings us to the start of our audio fingerprinting extraction algorithm. So the audio signal is first segmented into frames. And for each frame, a set of features is going to be computed. These features are invariant in nature to signal degradations. And 5 typical features that tend to be calculated for each frame would be the Fourier coefficients, the ML frequency substral coefficient, referred to as the MFCC, spectral flatness, sharpness, and linear predictive coding. But for our general example that we're going to be doing here, for our audio fingerprinting extraction algorithm, we'll be focusing on the Fourier coefficients that we have been seeing throughout the entire course. Derived quantities such as derivatives of these invariant features, means, and variances of the audio features themselves can also be used to get a little more reliability or more speed in actually calculating for the extraction. So visually what this looks like here is that we have the framing that occurs where we segment the audio signal into several frames, and then for each frame we perform the Fourier transform here. Once we have the Fourier transform, remember this is going to be a complex number in nature, so we find the absolute value. So the absolute value of each frame is then segmented here into band divisions, basically representing each frequency of the frame as of such. And then for each frequency of the frame, or each frame here that undergoes band division, energy computation, and bit derivation, we get our representation here known as Fn0, Fn1, and 31, where 0, 1, and 31 represents how many frames we actually are extracting up to. Now these features that we talked about in the last 2 slides can be mapped into a more compact representation using something referred to as hidden Markov models, or HMMs, or quantization. And this actually forms these frames when we do the segmentation of the audio signal themselves. However, one frame itself does not contain sufficient data to identify any audio clip, and that means we're going to have to use several frames to make up any fingerprint block accordingly. So the general streaming approach means that we need to extract 32-bit frames at 11.6 millisecond intervals. And any fingerprint block that we were trying to extract here is going to be consisted of 256 subsequent frames, where these 256 subsequent frames is going to give us a granularity of approximately 3 seconds. Because these are frames, and we're basically having to compute for each one of these frames need to overlap, like what we saw regarding in our previous lectures when we were doing the short time Fourier transform. So the overlap length is going to be 0.37 seconds, and it's going to be weighted by a Hannon window with an overlap factor of 31 and 32. In the worst case scenario, when we're doing the frame extraction and so forth, the frame boundaries used during the identification may be 5.8 milliseconds off, which is half of that of the 11.6 millisecond interval. The most important perceptual audio features from these frames are going to be in the frequency domain, so this is why we actually perform the Fourier transform to obtain the spectral representation of each of these frames. What we care about after we do the Fourier transform is that we need to get the power spectral density, or the absolute value, for each of these spectral representations for each frame. In extracting a 32-bit frame, 33 non-overlapping frequency bands are going to be selected, where the frequency range is going to be from 300 Hz to 2000 Hz, and they're going to be logarithmically spaced. The reason for this being is that the human auditory system, or the HAS, operates on approximately logarithmic bands. So we basically model this HAS system to match to our extraction system here. Energy differences, where we watch the sign of it regardless, is going to be robust to any type of processing in general. And mathematically, we can denote the energy of any band M of frame N as En, M, where the mth bit of the frame N is denoted as Fn, M. And the bits of the frame are formally defined by this equation here. It's important actually that you memorize this equation, for it actually may come up in your final exam. Bit errors, because we deal with bit strings, need to be calculated using the difference between the fingerprint blocks of the original and compressed versions of the song. And this is actually where we get our similarity measure. So the received audio that we obtain is going to be downsampled to mono audio with a sample rate of 5 kHz. And a simple downsample filter can be used without any performance degradation. So basically we tend to use 16-tap finite impulse response filters in order to obtain this downsampling. With regards to false positive analysis, 2 3-second audio signals are declared similar if the Hamming distance between the two derived fingerprint blocks is below a certain threshold t, where the Hamming distance is going to be the number of bit errors that is obtained. Statistically modeling these bit errors, we tend to see that they form a binomial distribution, where n of the binomial distribution is going to be the number of bits extracted, and p is going to be 0.5 or 50% for the probability that a 0 or 1 is extracted. This binomial distribution can also be approximated to a normal distribution to the large amount of bits used. And the threshold for the bit error rate, which is the most important feature that we're going to be discussing, is usually set to 0.35 or referred to as 35% error rate. So after we do all the extraction and so forth, the next part is actually how do we find the matches, which we refer to as our database search, where the most similar fingerprints needs to be found. Brute force searching is not going to be a viable solution because as our fingerprints database grows in the realm of millions and billions, it's going to increase in time to find these searches. And we can see here, basically, if the fingerprint database had about 10,000 songs with about 250 million fingerprint block comparisons, but each one of these songs had an average length of 5 minutes, this is actually going to take a very long time if we brute force this. So this isn't good. We're going to need a more efficient search algorithm. So the bit error rates can be calculated for a few candidate positions regarding these fingerprints. And these candidates contain with very high probability the best matching position in the database. In using the bit error rate calculation, the assumption is made that at least one frame has an exact match at the optimal position in the database. And this assumption is quite violated once we have heavily corrupted signals or heavily degraded signals. So this bit error rates strategy only works for good quality signals in particular. The fingerprint database will then in this case contain a lookup table with all possible 32-bit frames as an entry regarding for each one of these songs that we're trying to match. And every entry point is going to be a list with pointers to the position in the real fingerprint lists where the respective 32-bit frames are going to be located. Now in actual practice and implementation, a hash table is used instead of a lookup table. And in general, using the lookup table is tends to be 800,000 times faster than the brute force approach. The hash table is even way faster, and its performance varies, but it actually tends to be like 2 or 3 times of that of the lookup table. It can actually be even better, depending on the type of implementation used for the hash table. And there actually may be a more efficient way to prevent or circumvent errors for heavily degraded signals. But this actually is an ongoing field of research as to figure out how they can keep on improving the system for more accurate results and faster results. Now, a general way for improving the system is that when we obtain the frames, we actually can compare and threshold energy differences as we saw in a few previous slides. And if the energy difference is close to the stated threshold, it's reasonably likely that the bit was received incorrectly. However, if the energy difference is larger than the stated threshold, the probability of an incorrect bit is going to be low. And this method results in a very simple way to generate a list of the most probable frames by toggling only the most unreliable bits. The improvement isn't that spectacular, but it is still significant as to a speed up regarding the actual search and retrieve application itself. So this brings us to the end of our audio fingerprinting lecture, and for anyone who wishes to read a little bit more into actually how the audio fingerprinting system works, this is actually the reference for where the information was extracted for this lecture. And this also brings us to the end of all of lectures regarding the DSP course. So thank you for watching, and goodbye.